After what you read today, now you can see that because of d orbitals, some of the atoms that we use as central atoms may have 10 or even 12 valence electrons around them. Some of them can have even more, but the ones that we look at in this course aren't going to get any higher than that. So what you may be wondering is in figures 312 and 313, where did he even get these dot structures from? This is where the rule number 6 or step number 6 of how to draw Lewis structures comes into play. So I want to show you where these dot structures came from. Okay, so if I look at SF4, which is one of the first examples that he is showing you, and this is on page 82. Again, where did that dot structure come from? Sulfur has 6 valence electrons. Each fluorine has 7, and there are 4 of them, so that gives me 28 plus 6, which is 34 valence electrons. So again, how am I going to go about drawing that? So we choose the central atom, again, because of symmetry and because of electronegativity both. Sulfur is going to be our choice. I'm going to single bond everything else to this sulfur atom. So I'm going to have 1 fluorine, 2 fluorines, 3 fluorines, 4 fluorines. So that's 2, 4, 6, 8. Now I'm going to start adding lone pairs. Okay, so 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. 32, I have 34 valence electrons to use, so I didn't have quite enough. Even though that sulfur has an octet around it, the thing you have to remember is that sulfur is in the 3rd row of the periodic table. That means that with this 3rd energy level, it has d orbitals available to use, and that's what actually happens in this case. So if I have got an octet around these other things and I haven't used up all my electrons, then my extra lone pair is going to go on the central atom, and it's actually going to have 5 things around it. Okay, that is going to give this a trigonal bipyramid shape. It's actually going to have a seesaw shape because it does have 1 lone pair up here. Okay, if I look at ICl3, which is the next example that he shows you there. Iodine has 7, each chlorine has 7, but there are 3 of them. And so that is going to make a total of 28 valence electrons, okay? The iodine is the least electronegative, and again, for symmetry purposes, it would be obvious that that's the one everything else is going to be joined to. So I'm going to join 3 chlorines to that. So that gives me 2, 4, 6. Let's start putting lone pairs on. 8, 10, 12, 14, 16, 18, 20, 22, 24. I've got 28 that I need to use. If I go here, there's 26, and iodine now has an octet, but remember, it's got d orbitals that it can use to hybridize, and so that last lone pair can go here. Okay, so again, it has 1, 2, 3, 4, 5 items around that central atom, so it's called the electron geometry. The electron geometry is a trigonal bipyramid, but because 2 of those spots are taken up by lone pairs, it's actually called a T shape, which you can actually see that T right there. Okay, and then finally, he does I3 minus as his 4th example. So each iodine has 7, there are 3 of them, and I have this extra electron because of the ion, so that's going to give me 22 valence electrons. Okay, the only choice I have here is really to have 1 iodine as my central atom, and then, whoops, let's try to go on I properly, to join the other 2 iodines to it. So again, I've used 2, 4, going to start adding lone pairs, 6, 8, 10, 12, 14, 16, 18, 20. Everything now has an octet, but I need 22 valence electrons. So I'm actually going to scoop this pair over, and I'm going to put another pair up there to get my 22. Again, central iodine has 1, 2, 3, 4, 5 items around it. The electron geometry is considered a trigonal bipyramid, but because I've got 3 lone pairs taking the place of some of the bonds, this actually ends up being a linear molecule. You'll notice that I'm using a couple of words that he is not using. Again, one's called electron geometry, and it's based strictly on the number of things that are around it. So for all of these, every single one of these has a trigonal bipyramid electron geometry. But then if I actually look at the molecular geometry, that's where I look at just specifically the atoms that are there. So this one is a seesaw. And if you think about it, it's almost as if these two things are the legs of the seesaw kind of sitting down on the ground. And then these are the other parts of the seesaw that kind of tip back and forth like this. So that's why it's called a seesaw. This one was called T-shaped. Again, I think that should be obvious because it is in a T shape. And then this one is linear. Okay. All right. So that's where those 3 come from. Let's look at the sp3d2 because all of these are going to be, all of these are sp3d hybridized because they have 5 items around them. Let's look at the other examples that he gave you because they are now going to have the sp3d2. So let's just make sure that we're clear on how to draw those structures. The first one that he does is IF5. And so iodine has 7 valence electrons. Each fluorine has 7. And there are 5 of those. So that actually gives me 42 valence electrons. Okay. Iodine's going to be central. So iodine goes here. So I'm going to have 1, 2, 3, 4, 5 fluorine. So I've used 2, 4, 6, 8, 10 valence electrons so far. Let's start filling in with lone pairs. So I've got 10. Let's make sure I count right. 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. Everything certainly already has an octet. Iodine already has more than an octet, but I still have 2 valence electrons that I haven't used, and so I'm going to put them on my central atom. Okay, so this iodine now has 6 items around it. So this is going to be sp3d2 hybridization. The electron geometry for this is octahedral. However, the fact that I've pulled one of these off makes this what's called a square pyramid. Okay, so octahedral electron geometry, because it has 6 items around it. But molecular geometry for this is going to be, what did I say it was? Square pyramid. Square pyramid molecular geometry, because it has one of those bonds missing. It has an electron pair there after all, or instead, okay? ICl4 minus, okay? So iodine has 7 valence electrons. Each chlorine has 7. There are 4 of them, plus 1 more. And so that's going to give me 36 valence electrons. Okay. Again, iodine's going to be central. We'll do this quickly here. I've got 4 chlorines attached. So I've used 8 electrons so far. 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Everybody's satisfied. Everybody has an octet, but I've got 4 valence electrons I haven't used. And so I'll put two lone pairs stuck on that central atom. Again, an octahedral electron geometry. However, the molecular geometry of this one is going to be square planar. Okay. One other thing I'm going to go ahead and mention to you, just in case as you're doing a couple of the labs that I've given you, if you want to try to draw these in 3D structure with what you're seeing online, with the lab simulation that you're going to be using, I'm going to show you how to do this. So if you have SP3D, and it looks like my marker's giving out, so let me get something that's going to be a little darker here. Sorry about that. Want to be able to make sure you can see this. So if I have an SP3D hybrid geometry, if my central atom is here, then a lot of times the way that I'm going to draw that is I'm going to draw these atoms going straight down, straight up, and I think I may have mentioned this before. One of them is going to go straight out. One of them is going to look like it's behind the plane of the board. And the other one is going to look like it's coming out straight in front of the plane of the board. Okay? So if you want to draw it in 3 dimensions, that's how you're going to go about doing that. Okay? Again, from here to here, this is a 90-degree angle. And these guys here are 120 degrees apart because these 3 are cutting on through the plane of the blackboard this way, whereas these are in the plane of the blackboard. Okay? And then you may, take some of these off and put lone pairs there if you need to do that for whatever you're drawing. For the SP3D2, again, the way to draw this one 3-dimensionally, if this is your central atom, you're going to draw one up, you're going to draw one down, and then the rest of them, again, are going to be perpendicular to the plane of the board. And so this one is going to be behind the board. This one is going to be sticking out in front of the board. This one will be back behind the board. This one is going to stick out in front of the board. So that's how you're going to draw that 3-dimensionally on a 2-dimensional surface. Okay, and then you may have to, again, well, you wouldn't do that one. If you needed to rearrange those so that you had an electron pair, you're going to pull these guys off first. Okay, all right, so hopefully that will give you some clarity as to how to draw these. If you have to start adding electron pairs to that central atom, shows you how to use that 6th step of what we talked about in drawing Lewis structures.